Hello everyone, this is Lecture 9 of ComSci 142, Minimum Spanning Trees. In this video, we will discuss two minimum spanning tree algorithms, namely Prim's algorithm and Kruskal's algorithm. So let's start with an introduction. Let's imagine that this is a road network for a certain province. The vertices are the towns, and the edges are the roads that connect the towns. The edge weights represent the length of that road that connects the two towns. So for example, the edge CD with edge weight 9 means that there's a road from C to D that's 9 kilometers long. Okay? Unfortunately, one day there was an earthquake that destroyed all of the roads. Now, as the governor of the province, you would want to repair all of the roads eventually, right? However, since you are racing against time, you need to choose or pick which roads to prioritize such that all of your towns could be reachable. Okay, so let's say for example, in this graph, you would maybe want to prioritize the road from C to D here, because otherwise D, the town D is not reachable, right? Because this is the only road that leads to town D. So with the same reasoning, we also need to prioritize the road from F to G, because otherwise town G would not be reachable. Okay? Now, the road from E to H is only 3 kilometers long. So if it's a shorter road, then it would maybe also finish faster, right? You could repair that faster. So maybe we could also prioritize this one. Okay, E to H, right? But you can't reach all roads yet. All towns yet, right? So maybe if I also repair A to C, which is only 5 kilometers long, so I will also prioritize this one. And then to reach B, if I pick between the AB or BC, then I would pick AB because it's only 6 kilometers long, right? Now, at this point, you can now reach A to B, and then from here you can also reach C and D, right? Now, let's take a look at the edge from B to C. Should we also repair this one? Now, maybe later we could, but for now, this is not a priority because town B is already reachable, same with town C, right? So, if we prioritize this one, that would already be redundant, okay? That would, the workforce that you would have used for this road, you could have used that elsewhere to finish it faster, right? So, we would not prioritize this road because anyway, town B and town C are already reachable, okay? So, after that, maybe we could also repair the CF road so that it would link up A, B, C, D with F and G. So now, A, B, C, D, F, G are already connected. However, the two towns here, E and H, are still isolated from the rest, right? Because there is no road that connects E and H to the rest of the towns, assuming that all of them are still broken. So out of the remaining 3, 14, 8, and 10, maybe I would prioritize this one because this is only 8 kilometers compared to the others, which is 14 and 10 respectively. So with this set of roads that I picked, I could now reach all towns for now. Okay, so I didn't even need to repair this one, or this one. Okay, so for now, that would be my focus. Okay, so this would be our solution for this problem, and that would be that's essentially how spanning trees work. Okay, so formally, for a spanning tree, you're given if you're given a graph G with vertices V and edges E, the spanning tree is a subset of the edges E. Okay, so you pick some edges, so it's a subset, and those edges will form a tree, and those edges connects or spans all the vertices V. So that is a spanning tree. So going back here in our introduction example, we picked a set of edges, okay, subset of edges. So we did not pick all edges, okay. You could also pick all edges, but then some of them would be redundant, okay. So you only pick a subset of edges that connects all of the vertices. So all vertices are covered by at least one edge. So you'll notice all of them are connected through one edge that we picked. Okay, so that is the idea for a spanning tree. Now for minimum spanning trees, this is when you have edge-weighted graphs. So earlier, our edges have weights that represent the length of the road. Okay, so for edge-weighted graphs, the minimum spanning tree is the spanning tree whose sum of edge weights is at minimum. So you just get the total of the edge weights and you try to minimize that. And the spanning tree with the minimum sum or the minimum value would be your minimum spanning tree. Okay, so we are interested in getting the minimum cost because just like in our example of road repairs, a big cost in that edge is probably not what you want. Okay, you would want as the lowest cost as possible. Okay, however, in some cases, some graphs could have multiple minimum spanning trees, especially if there are repeating edge weights or if the edge weights are not unique. So let's say that there is an edge from B to C that is of length 4, and then there's also one from B to H of length 4. So maybe you could choose between the two, and picking one would form one minimum spanning tree and picking another one would be another minimum spanning tree. So MSTs are not unique, especially if the edge weights are also not unique. Okay, so some properties for the MST or minimum spanning tree. First, it's acyclic, so there are no cycles, because if it's a tree, then there should be no cycles, right? Because remember, trees are acyclic. And then an MST is also connected, so that means that there is only one connected component. So there should exist a path between each pair of vertices. So there should be no vertex that's left out of the component. Okay, so it should be connected. So some assumptions that we need to make to make our algorithm easier or more straightforward. Let's assume that the edge weights are unique at first. But if they're not unique, at least assign a tiebreaker so that your algorithm will be straightforward, okay, and doesn't have to choose. Okay. Let's also assume that the graph is connected. It's only one component, so that there would be a minimum spanning tree that exists. Because if the graph is not connected, then obviously there would be no MST, because for an MST you need to span all vertices. But if there is one vertex that is not connected to the rest of the vertices, then you cannot span all vertices, right? There's just no way to create an MST if the graph is not connected, if there are multiple connected components. Okay, so remember that if you just want undirected connectivity, assuming that our graph is undirected, you can just run the breadth first search, BFS, to check if the graph is indeed connected, right? So you could do that as a pre-check to make sure that everything is connected. If the graph is not connected, then we cannot create a minimum spanning tree, but instead we could create something called the minimum spanning forest. Okay, so MSF. So an MSF or a minimum spanning forest is just collection of MSTs. So if your graph is disjointed or disconnected, then there would be multiple connected components. And for a minimum spanning forest, each connected will just have its own MST. Okay? So it's a collection of MST. So it's pretty straightforward. A forest is just a collection of trees. So that's just the difference. Okay? But again, for our discussion here, let's just assume that the graph is already connected. Okay? Now, why are we interested in the MST problem? So these are some applications. Whenever you want to connect a set of points using the minimal amount of connection, then MST is applicable. So examples of points would be cities or homes or computers, and the connections could be roads for cities. Homes could be connected with wires and pipes for water and electricity. Then computers, the same thing, wirings for the network. So if you want the minimal amount of connection that would connect all points, then MST is um, your is the problem that you're looking at. Okay, so for MST, there is a generic MST algorithm that exists. So Prims and Kruskals actually follows this generic MST pattern, just like how BFS and DFS also follows the generic graph search, right? So they remember that the generic graph search has a unspecified way of finding which node to expand next, right? So how do you get um, from the fringe? Should it be a stack or like a queue? Okay, so that's how PFS and DFS differed. And then for MST, that's more or less the same. There is a general pattern or the general flow of the algorithm. And then Prims and Kruskal's will just differ on a few things, okay, on a crucial part of the algorithm, because it's um, left, what do you call this, unspecified. Okay, so there's an unspecified part in the generic MST, and then that's where Prims and Kruskal's will come in and apply their own technique on how to do that one. Okay, so let's start with the generic MST algorithm first. And what it does is it will maintain an intermediate spanning forest called F. So the spanning forest F would be what we will grow. Okay, so F would always be an acyclic subgraph of G. So there should be no cycles, because if it contains a cycle, then that won't be an MST anymore. Okay, and F is also a subgraph of MST, and eventually that forest will turn into the MST, because as we add more edges to the spanning forest, we're actually merging trees together that will form the eventual MST. Okay, so at the start, we our forest would consist of n one node trees. So how would that look like? So at the start, this would be something like this. Okay, so at the start, let's say there are 4 nodes. So at the start, your forest would look like this. So they are all individual trees, so one node trees. Okay, and then during the execution of the algorithm, we will be merging trees by adding edges between them. So maybe if we add an edge here, or we pick the edge here, then the 2 trees are connected. And then if we pick this one, they will also be merged. Then if you pick maybe something like this here, then they will also be merged. Then eventually there will only be one n node tree. So earlier there were n one node trees because they were standalone or individual nodes, and then eventually when we merged them, there's only one tree with n nodes. Okay, and that one tree would be your MST already. Okay, your minimum spanning tree. So that would be how your generic MST algorithm will flow. Okay, the question is, which edge should you add to the evolving forest? Because we said here that we will be merging trees by adding edges between them. The question now is, which edge should you add? Okay, so during the execution, we would be classifying edges into 3 things. It's either a useless edge, a safe edge, or an unknown or unspecified yet. Okay, so first, let's talk about useless edges. So a useless edge is when the 2 endpoints belong to the same component already. If that's the case, then that edge xy should not be part of the forest. Okay, the growing forest should not be an edge. So what do you mean by this? So for example, let's say that A, B, and C are already connected. So we already made these two merges prior to arriving at this iteration. And let's say that we are considering um, the edge from A to C. Okay, let's say that this is the next edge that we'll consider. Should we add this to our MST? Okay, should we merge these two as well? But take note that A is already connected to C because you can reach A to C using B as the intermediate node, right? So you can get from A, B, and then B, C. So these two are already connected and part of one component. So if you connect this two again using this edge, then that will already form a cycle. And if it's a cycle, then that won't be a tree anymore, because remember, trees are acyclic. So if it forms a cycle, you should not add that edge. Okay? So remember that MST is acyclic, as I've mentioned. Okay, so now the next type is something called the safe edge. And for safe edges, for each component of F, it's the minimum weight edge with exactly one node in the component. So since you want to expand or merge nodes together, you need to make sure that there's only one node in that component, meaning the two nodes in the edge don't belong to the same component. Okay, so maybe one node belongs to component A and then the other one belongs to component B. But if there are multiple, of course there would be multiple edges that belong to different components. Which edge should you choose? It should be the minimum weight edge, because of course we're aiming for the minimum total cost of the edges, right? So minimum weight edge with exactly one node in the component. So that would be your safe edge. Now, if it's sometimes you're also undecided on the edge type. It's not yet known whether it's safe or useless. Okay, so some edges could be undecided. So for a minimum spanning tree, it would contain all safe edges and no useless edge. Okay, because if there's a useless edge, that won't be minimum spanning tree, because if you remove that useless edge, it would still span the whole set of vertices, and for a much smaller edge cost, right? Total edge cost. So it should only contain safe edges. Okay, so for the generic MST algorithm, we'll repeatedly add safe edges to the evolving forest F, as I mentioned, and while doing so, if you add new edges to F, some undecided edges could become safe, and some undecided edges could also become useless. Okay, so the undecideds could become either safe or useless as we evolve and add more edges to our forest. Okay, so putting all of that together, it would look something like this. So T would be your spanning MST, and while T does not form a spanning tree, find the safe edge UV and you add that edge to the tree, and you repeat that until it forms a spanning tree. So it's pretty straightforward and not at all specific, because again, this is generic, right? So the specific MST algorithms would later on specify which safe edges to add, because in here we're only saying that you should find a safe edge. But if there are multiple safe edges, which safe edge should you add? Okay, so the specific MST algorithms that we'll discuss, Prims and Kruskals, will identify which safe edge should you add, and it will also describe how to identify new safe and edges and useless edges per iteration. Okay, so after one iteration, when you added that safe edge, which ones are useless now, which ones are safe again. Okay, so we will see that in the specific MST algorithms later. So let's start with our first one, which is Prims. Okay, now for the history of Prims, it's actually a really popular idea, or I wouldn't say popular, but yeah, the reason why I said popular is because there were multiple computer scientists who actually discovered, quote unquote, discovered this algorithm on their own independently. They didn't know that someone has already created this, or have already um, discovered also this idea. So Wojtek Jarnik, way back 1929, already described a similar solution. And then Joseph Kruskal also mentioned this in 1956. And then Robert Prim in 1957. And then Loberman and Weinberger again in 1957. And then Edgar Dijkstra, who's known as the father of computer science, also described this in 1958. There were a lot of people who described the same idea or the same solution for the minimum spanning tree problem, especially Kruskal. But since he also has another algorithm that he created, so they just named the popular name for this one is Prims. So because it's the I guess he was the second one to publish this one. Okay, but okay, before I discuss the algorithm steps, I'll show you an example first, because if I show you the example, it's easier to understand. Okay, so let's start with this graph, and these are our edges and edge weights. So how would Prim's algorithm work? So for Prim's, it always starts with a specific vertex, and that vertex could be any vertex. So you pick whichever vertex you start with. And let's say we start with A. And when we start with A, then A is already done. Next, we will need to find our safe edges. For our safe edges, those edges would be all edges wherein one endpoint is already done and the other endpoint is not yet done or not yet visited. So since we're done with A, okay, the endpoints that we'll consider would be AB, AC, and AD, because those are the edges with one endpoint being A that's already done, so this is already colored in yellow, while the other endpoints are yet to be visited. Okay, so those are the three edges that we'll consider. And then out of the three, of course, we'll pick the one with minimum weight. So that would be AB. And when we pick AB, this second endpoint would now be considered processed or done, because you've already spanned or covered B by choosing the edge AB. So now, the set of safe edges to consider would be different. And this time, that would be AC, AD, and BD. Okay, so earlier BD was not a safe edge, but this time it is, because B is now processed, right? And then AB was already done, so you don't consider that anymore. So AC is still an edge to consider because one endpoint is processed, the other one is not. AD is the same thing, while BD, as I mentioned, has one endpoint that's processed and the other one is not. So out of the three, we will pick BD because that has the minimum edge weight. And then we'll repeat again. So this time, is AD still a candidate edge? This time, it's not anymore because both endpoints of AD are already processed. So we don't need to consider AD anymore. What we need to consider would be AC and DC, because those are the two the edges wherein one endpoint still has an unprocessed edge, or sorry, vertex. So out of the two, we would pick AC because that has minimum weight. Okay? And after that, it's already done because you've already covered all four vertices. Okay? So you only needed three edges, so AB, BD, and AC. Okay? So that is how Prim's algorithm works. Okay? So for Prim's algorithm, it starts with one vertex, and you can choose any vertex, and then you grow the MST one edge at a time. So you grow it one at a time, and then you stop if all vertices are already part of the MST, if they're already covered. Okay. Since our goal is the minimum total weight, you will always select the minimum weight edge, okay, that will make the tree grow. So, which edge would make the tree grow? So that would be the edge where one node is part of the tree already and the other node is not yet part of the tree. So one where it's already processed and the other endpoint is not yet processed. Because if one is already processed, okay, so if one is already processed while the other one is not yet processed, okay, so this one is part of the tree already, the other one is not yet. So if we pick this edge, then we would be expanding the tree by adding this unprocessed node. Now, if the two nodes are already processed, then there is no point in adding this edge anymore because these two are already connected or part of the tree, right? So that would be useless. Okay, so putting all of that in a pseudocode, so your tree would be empty initially. You select an arbitrary vertex S to start the tree from, okay? And then while not all vertices are part of the tree, select the valid edges are the ones where one node is part of the tree and the other node is not yet part of the tree. So again, one node is already processed, the other one is not yet, okay? And then the safe edge would be the minimum weight edge from the valid edges. Then you add that safe edge to the tree and repeat until you span all vertices. Okay? So, it says here that we could select an arbitrary vertex S. Now, in our example earlier, we started with A. But what if we started with another, at another vertex? Let's say we started at D. Okay. If we start at D, the steps would be different because if we start here, then the set of valid edges would be different, right? So from here we could pick BD because this would be the minimum, right? And then from here the valid edges would be this three, and then we'd pick AB. Then from here we would pick AC. So we still got the same spanning tree even if we started at D. Now even if we start at, let's say, C, would still get the same spanning tree, right? So it's still the same wherever we start. Okay, so it doesn't matter where we start, you'd still end up with a minimum spanning tree anyway. Okay, now for the analysis, for the while loop here, okay, so for the while loop, this will run in at most n iterations because you're making sure that all vertices are part of the tree. So at the worst case, or actually it's every time, since all vertices have to be part of it, this would run in at most n iterations because you need to make sure that all vertices are part of the tree, right? And then for finding valid edges here, okay, and or finding the safe edge, so minimum weight edge from the valid edge, at the worst case you could be looking at all possible edges, right? So m edges at total, and then you get the min, so you need to traverse all edges at the worst case. So that would take m iterations, okay? So all in all, this would run in n iterations, and then each iteration has m work. So that would be O of mn running time. Okay? So while loop again is O of n, and then finding the safe edge needs to loop through all edges to find valid and min. That's O of m. So in total, that would be O of mn. Okay? For the memory, it's only constant because we didn't need to use any extra memory, right? Now, we could improve this performance by using the min heap na data structure. So remember the heap data structure from sorting algorithms, but in sorting we use the max heap, right? Wherein each parent has to have the biggest value out of the three with the left child and the right child, right? So it has to have a bigger value than its children. For min heap, it's the same but opposite, right? it's the same, but it's more or less the same idea, but it needs to be that the parent has to have the least value out of the three of them. So it has to have less value than its left child and its right child. So for the min heap, this would actually speed up our repeated minimum computations, because at each iteration we're supposed to find the minimum edge that is also valid, right? But if you do it in a min heap, it would speed up the min computations, because insert, delete, and extract min would only take log n. Okay, so in turn that would make the running time O of m log n, not mn. So it's faster by a bit. Okay, so you could use min heap to improve the performance of your Prim's algorithm. So let's see one more example of Prim's algorithm, this time using this graph. Okay, so let's go to graph 2, and let's just start with vertex A. So this time the the valid edges would be AC, AD, and AB, and out of the three, that would the safe edge would be AC, right? Because it's the minimum. After that, the valid edges would be AB, AD, CB, CD, and CF. So there's quite a lot, because C is connected with 3 other vertices. So that opened up new valid edges. And out of the minimum, we could pick this CD, right? After that, valid edges would be AB, CB, CF. Now AD is not a valid edge anymore, because the 2 endpoints are already done, and then we added a new one, which is DB and DF. Actually 2 valid edges. So out of this, how many? 5. There's actually a lot we could pick, right? Because there's a lot of ties, with 4 being the minimum weight. So as a tiebreaker, let's just go through it alphabetically. So maybe we'll pick AB. Okay. So after that, there would be only 2 valid edges na lang, because A, B, C, D are all processed already. So A, D, and C, B na edges are no longer valid. So it's only CF and DF. So out of the 2, CF is the min weight edge. So we'll pick that, and then after that, it's only EF that's left. So we'll have to pick that one. Okay, so that is now your minimum spanning tree. Okay, so the total cost of the minimum spanning tree would be 4 plus 1, 5, plus 2, 7, plus 9, 7 plus 9 is 16. Tama ba? Okay, yeah. So sorry, it's 3 a.m. in the morning when I'm recording this. Anyway, yeah, so that would be the minimum spanning tree. Okay, so that's minimum spanning trees. Okay, let's now go to our second algorithm, Kruskal's algorithm. And for Kruskal's, it's kind of more efficient on sparse graphs, when it's not a dense graph but a sparse graph. Okay, when there are only few edges. Okay, and there's a reason why that is later on. Now, Kruskal's also follows the greedy strategy. Now, I forgot to mention, Prim's is also a greedy algorithm, because why is it a greedy algorithm? Because we're always choosing the min weight edge that would grow the tree. So that is being greedy as well, right? Because you are selecting the minimum weight edge that it looks the best for now, and indeed that would also lead to your global optimum. Okay, so Prim's is greedy because you're always picking the min weight edge that would grow the tree. And then for Kruskal's, going back to Kruskal's is also a greedy algorithm, so it also picks the min weight edge, but this time it follows a different pattern. Okay, so it doesn't start with a particular vertex, unlike Prim's. So what it does is it would start with all vertices as their individual connected components, and then it would merge them together while eventually forming the MST. Okay, so what do I mean by this? So it's best shown with an example first again, so that you would know how it works. So let's start with this this graph. So as I mentioned, at first all vertices are their own connected components. So they are their own components. So I colored them differently here. So that means that they belong to different components. And then what we'll do is we will just go through each edge in ascending order of weights, because anyway we're picking min weight, right? So let's go through them in ascending order. So let's examine first ang AB, because that would be the minimum weight, right, with weight of 1. Now, considering this edge, if the two endpoints belong to different components, then we could merge them, right? Because anyway, they're different components. Like we can merge that by adding this edge to our MST. Okay? So since they belong to different components, then we can merge them. Okay, and we can pick this edge as part of the MST. And now I've updated the color of B to match A. So now they belong to the same component. And then the next edge that we'll consider would be DE, because it has a weight of 2. So again, we're just going through this in ascending order. So they also have different components, D and E. So we could also merge them. So now they're both red. Okay, or I don't know, that's salmon maybe. That's not exactly red. Okay, next one is the edge BE with weight 3, and they also belong to two different components, because this one is yellow, this one is salmon. So we could merge them, and now everything is yellow because we have now formed one component. The next one is 4, but they already belong to the same component, right? So, and if you add this one, this will form a cycle, so we will just skip that one. Then the next is 5, and 5 would connect BC, and currently they belong to two different components, so we could merge them, and that would be part of the tree now. And since everything is already covered, we are now done. Okay, so that is how Kruskal's algorithm works. So you don't start with a particular vertex, you just go through all edges in ascending order, and when the endpoints belong to two different components, you merge them. Otherwise, just skip, because they already belong to the same components. That would adding that edge would form a cycle. Okay, so pretty simple, right? So formally, we have the steps here. So start, each vertex is its own component. Then find the min weight edge UV. If the component U is equal to component V, then we'll skip. So if they belong to the same component, we skip, because that would add a cycle in the component. But if they belong to two different components, then we'll merge the components by adding an edge between them. So we are going through the edges in ascending order from min weight to max weight edge. Okay, so the safe edges are those edge nodes that are in different components. Okay, so if they are different, then it's safe to add them to the MST. Okay, so putting all of that in a pseudocode, it looks like this. So initially the tree is empty, and then the component dictionary will tell us what component that node belongs to. So for each node, initially the component of the node is the node itself, right? So because each individual node is its own component at the start. Okay, so they have different colors, right? And then we'll sort the edges in order of increasing weight, and for each edge taken in the sorted order, if the node 1 and node 2's component are not equal, then we'll add that edge to the tree, and we'll merge the two nodes components. Okay, so pretty simple. Now if we analyze this one, this one would take O of n if there are n edges, n nodes, because we need to look at each node and assign their own components. Now if you sort, this could take this, but you're sorting edges, right? So there are n nodes and m edges. You sort m edges would take m log m if you are using merge sort, right? And then for each edge taken in sorted order, so you're looking at each edge, so that would be O of m. Okay, and then merging the two nodes components, this could take O of n, because at the worst case you could be changing all of the you call this, all of the, or about half of the nodes components. Like for example, at the worst case it could look something like this, right? So maybe this is one component and this is another component, and then if you merge these two by adding this edge, maybe then let's say these are all component A, these are all component B's. When you merge them, you would have to change like half of them. So this is already the worst case. So if you need to change about half of the vertices, then that's O of n. Okay, ang pag-merge ng component. So everything, putting all of that together, that would be O of n at the start, and then plus m log m for the sorting, and then plus this loop runs in O of m, but each time you iterate, there is an O of n times O of n work per iteration. So this is O of mn. So in total, this would be O of mn, because this is the highest order. M log m is not the highest, it's mn. Okay? So, yeah. So sort edges take m log m for loop, because you iterate through edges once, that's O of m. And then you merge components, it's O of n. So in total, it's O of mn. Okay, running time. And then the memory is also O of n, because going back here, you actually need to take note of the component, and each node has to have a entry in the component dictionary. So that's O of n, the memory. Now we said earlier that this is efficient if the graph is sparse, and that's because we look through each edge at least once, right? We go through it in increasing order. So if there's only a few edges, then this would finish faster, right? So yeah, that's the reason why Kruskal is efficient for sparse graphs. Okay, so you could also improve the performance of Kruskal by using another data structure. This one is something called union find. Now you haven't encountered this one yet, so you could look into it if you want to. But basically for union find, you maintain a partition of a set of objects, and it makes it easier to find which set that object belongs to. So it has two main functions, or two main methods, union and find, of course, hence the name union find. So for union, if you take the union of set 1 and set 2, it will merge set 1 and set 2 into a single set, and then finding x will return the set that x belongs to. And the reason why we use union find for this is because that would allow us to find the component and merge components easily. And if we use union find, it would allow us to run Kruskal in O of m log n and not mn. Okay, so this is another example of using the right data structure would speed up the algorithm's performance. Okay, so again, the reason why we used union find is because, diba, we wanted to merge the two components when we need to when we add the edge between them. Okay, we merge the two different components, so that would be for union. Okay, set 1 and set 2. So that would merge them efficiently, and then when you want to find out what the components of the two endpoints are, then that's where find comes in. Okay, it will return the set that x belongs to, and then it will tell you whether the two sets are the same, because if they're the same, then they belong to the same component. Okay, so that's Kruskal's. Let's see one more example. This is actually the same example earlier sa Prims, but let's see how Kruskal's will solve it. So let's go to graph 2. So initially, again, they start with their own components, and they have there are 6 different colors. So let's go through the edges in ascending order. So we'll start with AC with 1. So since there are 2 different components, we will merge these 2. After that, CD with edge weight 2, and those are also 2 different components. We'll merge them. AD already belongs to the same component, right? So we'll skip. And then there's a lot of 4s, so let's just go through them in order. So AB, A and B still belongs to 2 different components, so we'll merge them. Okay. BC already belongs to the same components, we'll skip. BD we'll also skip. CF belongs to 2 different components, so we'll merge those 2. And then EF, 2 different components, so we'll merge. And after that, everything is already covered, so we're done. And this is the same MST that we found out when we used Prims. Kruskal's arrived at the same answer, but using a different method. So it didn't start with a particular vertex. It just went through all edges in ascending order. Okay, so that's it for Kruskal's. And yeah, so of course there are other algorithms for MST. Okay, one would be Boruvka's algorithm, the oldest minimum spanning tree algorithm. And then there's also something called the Karger-Klein-Tarjan algorithm that runs in O of M. So it's linear in terms of the edges, but this is a randomized algorithm. Okay, so it's not O of M all the time, but it's randomized. So this was fairly recent. And I say fairly recent, although it's about 20 years ago. Or actually, yeah, almost 30 years ago, actually. It's more than 20 years ago. It's because compared to the other MST algorithms, right, that was created in the 1950s, this one is fairly recent compared to them. Now, it's still an open question whether there is a deterministic O of M time algorithm. Okay, so it's a linear time algorithm for MST in terms of the edges that is not randomized, so it's deterministic. Okay, so it's still an open question. Who knows, maybe one of you could create the O of M time deterministic algorithm for MST. Who knows, right? Anyway, that's it. So to review, Prim's algorithm starts at a certain node, and then it will grow the MST. So it only keeps track of one MST. It will grow it one edge at a time, and it will add the safe min weight edge. So the safe edge is those that have or the valid edges are those that are wherein one endpoint is already part of the tree, the other endpoint is not yet part of the tree, and then out of those valid edges you pick the min weight edge, that is the safe edge. And then for Kruskal's, it doesn't start with a particular vertex, it just starts with all vertices as their own components, and it will grow a forest, right? So they could have like multiple spanning trees at once, and then we merge them eventually into one. And we do this by sorting the edges in increasing weight order, and then if we look at them one by one, and then we'll decide whether to merge them or not. We'll merge the two components if they are we'll merge the two endpoints if the two endpoints belong to two different components. Okay, so we merge the two different components. Otherwise, we'll just skip because it will form a cycle, and then eventually this will merge the forest into a single tree, forming the minimum spanning tree. Okay, and we also mentioned that the two algorithms follow the greedy approach because while creating the intermediate spanning forest F, it always is augmented at each step with some edge, but the edge that we choose always contributes to the minimum weight. So Prims, it chooses the minimum weight edge that is safe. Okay, and then sa Kruskal's, it's also greedy because it's ordering the edges from least weight to heaviest. Okay, so that's it. Now I'm leaving you here with 2 exercises, so you could pause the video here for now, and then you could maybe copy this onto a paper, or you can just work on it here and then try to figure out first on your own what would be the answer. So I will give you 5-second pause here, and then but of course you can pause the video on your own, and then I'll go to the solution. Okay, so I'm now going to the solution. So this is the solution, so please check if you got the correct answer. Now here's another exercise. You could try working or you could try using both prims and Kruskals here. So what would have been the steps if it was prims? What would have been the steps if it was Kruskals? So again, I will pause. You could pause the video here and answer it first before I show you the solution in the next slide. I'll give you another 5 seconds before I go to the solution. Okay, so if you're done, I will now go to the solution for both prims and Kruskals. So for the prims and Kruskals, this is the MST. Okay, but for the actual iteration steps, this is for prims. Okay, so check if you got the correct order. There are 8 iterations with total MST weight of 39. Then for Kruskals, it would be this one. Okay, so this is this order of weights, of edge weights processed. Okay, so also weight of 39. So that's it for this video, and if you have any questions, please don't hesitate to ask, and I will see you in the next video.